All right, the mammalian kidney or the renal organ. So, what type of organ is the mammalian kidney? It's a filtration reabsorption type organ, right? It's crescent shaped and has three major regions. You have the outer cortex right here. You have the middle portion, which is the medulla, and then you're gonna have this inner region, which is the renal pelvis. And this is like this funnel-shaped little part that's going to basically filter or just serve to collect the urine and feed it into the ureters and into the bladder, where it's ultimately going to get excreted out of the body. So, just a really quick basic rundown: cortex, medulla, pelvis, working outer to in. So, what is a nephron? It's the functional unit of the kidney. So, it basically is like the function of the kidney, at least in the filtration aspect, is being, in other aspects actually, is being totally controlled by this nephron here, which is this little thing that I'll get into. But just to note that there are 1 million nephrons per kidney. So this is a very small scale thing, and it's the combination of millions of these working at once to filter out to filter your blood in the kidneys. There are about 2 million total, 1 million per kidney, and here we have this little layout. This is a cortical nephron and a juxtamedullary nephron. For the sake of this layout in this like introduction, it is not really important to note what type they are, but it is important to note what portions of the nephron are located in what parts of the kidney. So the cortex. Cortex, again, remember the outer portion here, is going to have the Bowman's capsule, this round ball, and then inside of it there's going to be this glomerulus. And then we're going to have the proximal tubule and the distal tubule. Now, in the medulla, we're going to have this dip down in the medulla where we're going to find the loop of Henle and also the collecting duct. So the collecting duct and the loop of Henle are the medulla, and the rest of these portions are going to be in the cortex. Very important to know, especially for like histology and things like that. You're going to want to know where these different portions are located in the kidney. Filtration. Yeah, so that's the big one, huh? It's the big one that we're learning about when we talk about the kidneys. Filtration occurs in the glomerulus, which is a capillary tuft. So it's a tuft of capillaries, and the filtration is basically driven by the positive blood pressure in the glomerulus. So liquid components of the blood escape into the Bowman's capsule, into this. So they're going to escape out of this glomerulus into this round ball, this Bowman's capsule, where it's going to be start fed into the proximal tubule. And the important thing to note is that the Bowman's capsule does not allow blood cells or large macromolecules to pass through. Now, obviously, yeah, when we're filtering our blood, we're not trying to excrete our blood. So we don't want blood cells leaking through this glomerulus into the kidneys. We're not trying to piss out our blood. And these large macromolecules, these plasma proteins like albumin, we're trying to keep those as well. Those are very important for a lot of physiological functions. So big idea here is that the Bowman's capsule is not going to allow blood cells or large macromolecules to pass through. And it is also important to note that the glomerular capillaries are very leaky, because obviously if we want this urine or this primary filtrate to leak out of this glomerulus into this Bowman's capsule, we're going to need some quite leaky capillaries for that to happen. Also, something that will come up later is the podocytes, or the foot processes. These pedicles form part of the filtration structure, along with the fenestrations of the endothelium and the glomerular capillaries. And that's going to be explained a little bit better on the next slide, but basically the glomerular filtration barrier, what we were talking about here. So quick just definition here. The primary urine is the initial ultrafiltrate produced in the Bowman's capsule and is roughly isoosmotic to the blood. So osmolarity wise, it is going to be about the same as blood, but the composition is not the same, and that's going to come up in I think the next slide. But here we can get a very good look at like at what levels these filtrations is occurring. So let's work from our way out. We're going to come through the renal artery. This blood is going to be fed into these afferent arterioles. Blood flow is coming in this way into these capillaries. This is the glomerular capillaries, right? So we have the glomerulus here. The blood pressure from the afferent arterioles is going to be pushed into these capillaries, and the positive blood pressure is basically going to press the blood through these capillaries into the Bowman's capsule. Not the blood, actually. Of course, we're keeping the red blood cells, but it's going to press this primary urine out into this Bowman's capsule. So blood flows in, coming in here, and then here we can see the filtration. So the blood is coming in. First level of filtration is it's going to pass through these fenestrations in the actual endothelium of the capillaries, these pores. It's going to be filtered. Basement membrane, mostly structural, but also playing some role in filtration. And then ultimately the third part right here, it's going to be pressed through these slit diaphragms and these foot processes. So it's being filtered here, and filtered through here again, where it's also going to exit into this Bowman's capsule and then into the primary or the proximal tubule. Blood cells and proteins are retained in the blood. So right here, you have your blood proteins and your red blood cells. They're going to stay in here. They cannot press through these filtration barriers. They're too small. Very important. Now, blood volume removed per pass is about 15 to 25%. And so that gets us to the definition of the glomerular filtration rate. And so in humans, about 7.5 liters per hour for a 60 kilogram body mass individual for both kidneys. That's a shit ton of filtrate. 7.5 liters. So yeah, this poses the question: how can you sit through a lecture without your bladder rupturing if you're producing 7.5 liters per hour? That's gonna get explained on the next slide. That essentially the filtrate that's initially produced is not what is being excreted at all. There's gonna be very ultra concentrated down the line, and it's gonna be a lot lower once it exits the body. And again, just to drive it home here, the positive blood pressure is the driving force for the filtration in the glomerulus. So we see that we have an oncotic pressure gradient here, 30 milligram or 30 mm, and we have this lumen. The lumen of the capsule is 15 mm with the hydrostatic pressure, and we have this 60 and the blood pressure in the glomerulus. So 60 pressing or 60 coming into the glomerulus. Even with a subtraction of 30 and 15 coming this way, we're still having a positive net of 15 filtering the blood through this filtration barrier. Also important to note that the ions in the primary urine are not the same composition as in the blood. So the ions in the Bowman's capsule are in Gibbs-Donan equilibrium with the plasma, which has a slightly negative potential due to the negatively charged proteins retained in the plasma. So what does that mean? So the ions in the Bowman's capsule here are in Gibbs-Donan equilibrium with the plasma, and the plasma is more negatively charged because proteins retained in the plasma. Proteins are negatively charged, and they're going to stay. Again, remember, large macromolecules like proteins cannot go through the filtration barrier, so we're going to have these proteins retained in here, and they're going to be negatively charged, and then we're going to have our urine outside, which is going to be not as negatively charged, but they are in Gibbs-Donan equilibrium because these ions are permeable to this filtration barrier and will move in sequence. Will move to equal out the charge difference between the two, but it is just important to note that the composition is not the same as in the blood. So, reabsorption of fluids and solutes. What is reabsorption? Reabsorption is basically we formed our primary urine here, and here we have the proximal tubule. Reabsorption is when a lot of these important things like these solutes like sodium chloride, potassium, calcium, glucose, amino acids, urea, choline, all of these were filtered out initially, but they're going to be reabsorbed back into the blood. And 70% of this occurs in the proximal convoluted tubule, or the first portion of the nephron. So we formed the primary urine here. We filtered all these things out, but then it reached the proximal tubule, and hey, we need these things. They're very important. So they're going to be reabsorbed back into the blood. So let's see. Proximal tubule reabsorption begins. Active transport of sodium. So we're actively transporting, using energy to bring sodium back into the blood, because very important. and freely permeable to water. So a lot of the water is going to also freely flow back into the blood. Then we have the loop of Henle. So once this proximal tubule hits, we have this descending limb and this ascending limb, and it's ultimately going to create this loop of Henle, which remember is in the medulla. As you can see here, the white portion here, this is we're going from the cortex and we're dipping into the medulla with this loop of Henle. The loop of Henle is divided into the descending thick, descending thin, and ascending thick. So descending thick, descending thin, ascending thin, ascending thick. And in the loop of Henle, minimal net reabsorption of water. So we have a lot of water reabsorption here, which again, that's why when I said earlier that while the initial filtrate is 7.5 liters, we're absorbing a lot of that water back into the blood just in the very first portion in the proximal tubule. So it's not going to reach the ureters. We're reabsorbing a lot of water and different molecules in the proximal tubule. But also important to note that there's not very much net reabsorption of water in the descending ascending limb or the loop of Henle. Then we have the distal tubule right here. This is where reabsorption is completed for most solutes. So at this point, most of the solutes have been reabsorbed into the blood, and the distal tubule is actually where the secretion system occurs. So that's basically secretion is when we're going to get transport of solutes back into the nephron to be excreted. And then, of course, at the end here, we have the collecting duct. And a collecting duct actually drains multiple nephrons. So we have this collecting duct at the end, and it's going to drain multiple different nephrons. And water reabsorption here, is very hormone dependent. It's going to play a large role. We're going to talk about some hormone that really depends on the reabsorption of water in the collecting duct. And so roughly less than 1% of the filtered volume is eliminated in final urine. That's why I said, yeah, we initially produce 7.5 liters, but less than 1% of that is actually going to be eliminated as final urine. By the time the filtrate has reached through all of this and all of this reabsorption has occurred, the urine is very concentrated and a lot smaller, a lot less volume. So the loop of Henle. So this is when we're going to get into the idea of a countercurrent multiplier system. So the loop of Henle acts as a countercurrent multiplier to create an osmotic gradient in the medullary tissue to facilitate water removal from urine by the collecting duct. So the loop of Henle itself does not concentrate the urine. Okay, so only a very modest amount of water are actually removed from the loop of Henle, but considerable quantities of salt are deposited in the medullary interstitial space. So what does this mean? Well, here we have the descending portion of we have the descending limb and this loop of Henle, and right here it is permeable to water, so water is going to be exiting, but the salts in the ions are going to be concentrated and not allowed to leave. So we're essentially concentrating the urine very heavily right here, and the water is coming out, and it's going to be very high salt content, very high osmolarity right here, and then we're going to reach the ascending limb, where it's very low permeability to H2O. So we still have a very concentrated urine right here, but now we're going to start pumping these salts into the medullary tissue. So we're going to concentrate the salts here, lose water, and then we're going to pump all of those salts out into this medullary tissue, and then the water is going to eventually reach the distal tubule. And the reason that there's not a much net change in the water itself is because it is very permeable to water here, so we're losing a lot of water here, but then we're losing a lot of salts here. So the actual urine itself is not being concentrated in the loop of Henle. It's actually this osmotic gradient that is created in the medullary tissue that is going to cause the concentration of the urine ultimately in the descending duct. So fluid movement must be continuous for a countercurrent multiplier. The change in osmotic concentration along the length is far greater than the difference in one limb to the other. So the difference between the two sides of each limb, or these like evenly, are going to be about the same, but as you get deeper, the gradient is going to change drastically, multiplying, essentially getting this larger osmotic gradient. And also it does need to be asymmetric, where there's high permeability of water here and active transport of salts here. Now, the real reason that this is important